40 light years out, astronomers spotted a world that checked every box solid ground close to Earth's size, sitting at a temperature where water could stay liquid. For nearly a decade, the scientific community treated it as the leading candidate for life outside our solar system. So they turned humanity's most capable space observatory toward it. The James Webb Space Telescope, a $10 billion instrument that took 3 decades to build engineered. In large part to answer one question: is anyone else out there? After years of watching, after wrestling with data, so tangled that whole teams worked in shifts and had to invent entirely new mathematical tools just to make sense of it, the result came back, neither yes nor no. It came back as something stranger they simply cannot tell. Not because the hardware failed, not because the planet sits too far away. The culprit is the star. This planet circles its misbehaving in a way almost no one saw coming, and it's quietly undermining the whole method. Stick around, because what's unfolding at this star is one of the strangest and most consequential stories in modern astronomy. The planet is TRAPPIST. To understand why it captivated every astronomer on the planet, the moment it was found, you first have to understand its home system. 40 light years sounds distant, but our galaxy spans roughly 100,000 light years, so in cosmic terms, this star is essentially next door. It's called TRAPPIST-1, a small, dim red star, roughly Jupiter-sized physically, yet dense enough to sustain nuclear fusion. Orbiting tightly around it are 7 rocky, roughly Earth-sized planets. Their orbital periods are almost absurdly short, the innermost circles. Its star in about a day and a half, the outermost in just 19 days. Every one of the 7 sits closer to its star than Mercury sits to our sun. The whole system star included would tuck comfortably inside Mercury's orbit. That proximity sounds lethal, but here's the twist. TRAPPIST-1 is nothing like our sun. It's faint and cool, so faint that you'd need to stand roughly at Mercury's distance from it just to feel the warmth we feel here on Earth, because the star is so weak its habitable zone. The band where liquid water could exist on a surface sits unusually close in, and 3 of the 7 planets labeled E, F, and G fall right inside that zone. No other known system offers 3 potentially habitable Earth-sized worlds packed close enough together that a telescope could realistically study their atmospheres dozens of times a year. That's what made this system front-page news in 2017 and why it landed near the top of Webb's target list the moment the telescope launched on Christmas Day 2021. The discovery story is nearly as remarkable as the system itself. Belgian astronomer Michael Gillen was running a survey from the Chilean Atacama Desert, not with a giant flagship observatory, but with a modest 60-centimeter robotic telescope, had nicknamed TRAPPIST, a nod to the Trappist beers of Belgian monasteries. He was scanning about 50 nearby ultra-cool dwarf stars for the telltale dimming of a planet passing in front of its star. Around the 30th star on his list, something showed up, a dip, then another, then a cluster of dips too, frequent and regular to belong to just one object. Multiple planets were transiting. Gillen pulled in observatories on several continents, all aimed at the same faint red star. And in May 2016, his team announced 3 Earth-sized planets around it. Notable, but not yet the full story. The real breakthrough came when NASA's Spitzer Space Telescope stared at the star continuously for 21 straight days. Buried in that data were 4 more planets the ground-based telescopes had missed entirely. By February 2017, Gillen's team had the complete picture. 7 rocky Earth-sized worlds around one star, 3 of them inside the habitable zone. The way these 7 planets orbit in just crowded it's mathematically precise, and in a way that reveals the system's history, all 7 lock into what's called a resonant chain for every 8 orbits. The innermost planet completes. Its neighbor completes almost exactly 5, and so on outward. It's the longest unbroken orbital resonance chain ever documented around a single star. The planets likely drifted inward through their birth disk of gas and dust billions of years ago, locking into this rhythm like beads settling onto a wire. A rhythm that's held for an estimated 7 to 6 billion years, making the system roughly 3 billion years older than our own solar system. That same resonance let astronomers do something remarkable, weigh each planet precisely, despite never seeing more than a faint dip in starlight. As the planets tug on each other gravitationally, their transit timing shifts by seconds or minutes from what simple orbital math would predict. Measuring those tiny shifts let scientists calculate each planet's mass, and the numbers confirmed. These are genuinely rocky worlds with solid surfaces, not gas balls or bottomless ocean planets. TRAPPIST-1e sits squarely in the habitable zone's sweet spot, absorbing about 2/3 of the stellar energy Earth gets from the sun. Right size, right temperature, rocky composition on paper. The best Earth analog candidate ever identified, Webb was built in part to study exactly this kind of world. Here's the plan scientists had when Webb launched as TRAPPIST-1 when E crosses in front of its star. Starlight filters through the thin edge of its atmosphere. Different gases, water, carbon dioxide, methane, oxygen, sulfur, dioxide, each absorbs specific wavelengths, leaving a distinct signature in that filtered light. Read those signatures and you know the atmosphere's composition, all without sending a probe anywhere near the planet. The technique already works beautifully on large gas giants with thick atmospheres. The open question was whether it could work on a small rocky world whose thin atmosphere would produce a signal roughly 100 times weaker. For TRAPPIST-1e, the answer so far, not yet. And the reason is the star itself. TRAPPIST is magnetically unstable. Its surface is a patchwork of dark spots and bright, hot regions that shift constantly as it rotates. The sun has sunspots too, but the sun is big and bright enough that they barely matter for transit measurements. TRAPPIST is small and dim, so those spots and bright patches cover a large fraction of its visible surface, and that surface can change noticeably even within a single observation. That matters because transit measurements work by comparing the star's brightness during a transit to its brightness outside one. Any shift in the star's surface creates a false signal that mimics an atmospheric absorption feature, something researchers call stellar contamination. On TRAPPIST-1, that contamination reaches amplitudes of hundreds to thousands of parts per million, while the atmospheric signal researchers are hunting for tops out around 100 parts per million. The noise outweighs the signal roughly tenfold, like straining to hear a whisper across a stadium during a live rock concert. Worse, this isn't random noise you can filter out. It mimics the same wavelength patterns as the very molecules scientists are searching for. To compound things, a powerful stellar flare erupted mid-transit during one Webb observation of TRAPPIST-1e, injecting a massive unrelated signal into the data and ruining that entire observation. Researchers spent over a year building new mathematical frameworks just to try separating stellar noise from any possible planetary signal. Even after all that work, the honest answer remained they couldn't say with confidence whether TRAPPIST-1e has an atmosphere at all. While the campaign on TRAPPIST-1e fought stellar noise, Webb's observations of the system's other planets came back far cleaner and far bleaker. TRAPPIST-Y, the innermost world, was examined first, using Webb's MIRI instrument measuring thermal emission at a wavelength where carbon dioxide absorbs strongly. A thick CO2 atmosphere like Venus has would have dimmed that thermal signal noticeably. Instead, the reading came back bright and clean. Ruling out a thick atmosphere with greater than 6 sigma confidence, meaning the odds of this result being a fluke are roughly 1 in 500 million. TRAPPIST-1b is a bare, airless rock. TRAPPIST-1c showed a similar pattern, pointing strongly away from a thick atmosphere, though with somewhat less certainty. Then, in April 2026, a paper in Nature Astronomy delivered full thermal phase curve measurements, tracking brightness as each planet rotates and shows different faces to Webb for both B and C together. Both worlds emitted heat, consistent only with bare rock, ruling out even atmospheres as thin as Earth's. Next came TRAPPIST-Sodite, sitting at the inner edge of the habitable zone, and slightly smaller than Earth, considered the best remaining candidate for having held onto some air results published in 2025, showed a transmission spectrum that, once corrected for heavy stellar contamination, came back essentially flat. No methane, no water, no carbon dioxide, no carbon monoxide, no sulfur dioxide. The lead researcher summarized it bluntly. TRAPPIST-1d is no longer a candidate, Earth twin. 3 of the 7 planets, bare rock stripped of whatever atmosphere they once had by their star's radiation. That leaves the entire weight of the search resting on one remaining world. TRAPPIST-1e is the one habitable zone planet where the numbers still work, if it has an atmosphere at all. In late 2025, there was a moment that felt like a breakthrough. Researchers ran their contamination-corrected transmission spectrum of TRAPPIST-1e through a range of atmospheric models, and found that models including methane fit the data slightly better than those without it. Not a firm detection, a statistical lean, a hint that the planet might carry traces of methane in a nitrogen-rich atmosphere, something like a warmer version of Titan Saturn's moon. The team floated the phrase warm exotitan, and for a moment it looked like the data was finally pointing somewhere. Then Sucrit Ranjan, a planetary scientist at the University of Arizona who'd co-authored all 3 of the team's papers, spotted the catch. TRAPPIST is cool enough that methane can form in the star's own outer atmosphere, not on any planet, but in the star itself. And methane sitting in a cool red dwarf's atmosphere leaves a spectral signature nearly identical to methane in a planet's atmosphere 40 light years away. So when Webb picked up something that resembled methane, there was no way to know if it came from the planet's thin atmospheric shell or from the star's own contamination. Ranjan's read was direct. The tentative methane signal is more likely stellar noise than a genuine detection. But he was careful to note that this doesn't rule out an atmosphere on TRAPPIST-1. It only means current data can't distinguish a real planetary signal from a stellar artifact. Two possibilities remain on the table: a bare, irradiated rock like its inner siblings, or a thin, nitrogen-based atmosphere, too faint for Webb to confirm. Cleanly, what is ruled out is a thick, hydrogen-heavy envelope like a mini Neptune. Webb had more than enough sensitivity to exclude that whatever TRAPPIST-1e is, it's evolved past that stage. It resembles Earth or Venus far more than a puffy gas world, which one, though, is still buried in the noise. Here's where the story turns clever. If the star is the source of the problem, and every observation confirms, it is then the fix has to target the star directly. Researchers landed on an approach that sounds almost paradoxical, using a dead world to help find a living one. TRAPPIST, Pomdine already confirmed as a bare, airless rock transits the same star as TRAPPIST-1, because B has no atmosphere of its own. Anything showing up in its transit spectrum has to come from the star, every spot, every bright patch, every molecular fingerprint from the star's own atmosphere. That makes TRAPPIST-1b a built-in calibration tool. The approach called the dual transit method works by observing both planets' transits close together in time, recording the stellar contamination pattern from BS transit, then subtracting that same pattern from S spectrum. Whatever's left over signal that the star's contamination can't explain either points to an atmosphere on E or its absence. Either outcome would be a major result. Early tests in 2024 and 2025 showed the method genuinely reduces stellar contamination as intended, but there's a catch. It assumes the star's surface stays roughly stable between the two transits. When a flare erupts in between, which happens often on TRAPPIST-1, the star's face effectively resets within minutes, and the contamination pattern captured from BS transit no longer matches what E experiences during its own. The tool breaks down exactly when it's needed. Most researchers are pushing forward anyway, with a planned program of roughly 15 dual transit observations spread across multiple Webb observing cycles, betting that enough data points will average out the noise from individual flares. Ryan McDonald, one of the researchers on the project, has estimated the next major update on TRAPPIST-1Re's atmosphere could land sometime in early to mid 2027. Beyond Webb, other tools are being built specifically for this problem. NASA's Pandora mission. A small satellite designed to watch host stars in near-infrared and visible light before, during, and after transits is built to map stellar noise so it can be subtracted more precisely. 3 extremely large, ground-based telescopes currently under construction aim to separate stellar and planetary signals using their slightly different Doppler shifts. Further out, NASA's habitable worlds observatory, targeted for the 2040s, is designed to directly image potentially habitable planets by blocking out their host stars' light by a factor of roughly 10 billion, not inferring the planet from starlight, but isolating the planet's own light outright. In January 2026, NASA awarded technology development contracts to 7 companies to start building the engineering this would require. So where does this leave things? 40 light years away sits a planet that may or may not have air orbiting a star that keeps drowning out the very signal scientists are trying to detect. 3 of its 6 sibling planets are confirmed dead rock, and that fact alone carries weight. Red dwarfs are the most common star type in the galaxy, and evidence is mounting that when young they're violent enough to strip the atmospheres off their closest planets entirely. The habitable zone worlds that keep their air, if any do, may be the exception rather than the rule. If TRAPPIST-1E turns out to be another bare rock, the implications ripple outward. The most common type of potentially habitable real estate in the galaxy, rocky planets around red dwarfs, might not be habitable after all. That would mean life, if it exists elsewhere, likely needs a sun-like star, making it rarer than hoped. If TRAPPIST-1E does turn out to hold even a thin atmosphere, the opposite follows, since red dwarfs make up roughly 70 of the Milky Way's stars each. With the potential to host its own tight cluster of rocky worlds, the number of places life could take hold becomes almost incomprehensibly large. One planet, one unanswered question. And the answer to whether we're alone in the universe may hinge on what's hidden in the static around one small, restless red star. 40. Light years from home, we built the most powerful telescope ever made. We pointed it at our best candidate for life beyond Earth, and the star it orbits is shouting loud enough that we still can't make out what the planet is trying to tell us. The answer is in there, somewhere. We just haven't figured out how to listen for it. Yet.